Have you ever stopped to wonder why your hot coffee eventually gets cold? Or, why sand on the beach can absolutely scorch your feet on a summer day? Well, it's all happening in this invisible world of heat and thermodynamics. Today, we're going to crack the code on how all of this stuff works, from the cup in your hand to the entire planet's climate. Let's get into it. Okay, so it all kicks off with a really simple question. You've got 2 spoons, right? You stick them both in a bowl of hot soup. One feels like it's going to burn your hand right off, but the other one? It's totally fine. Now, they're both in the same soup, so they're at the same temperature. So what gives? Let's figure this out together. To solve our little spoon mystery, we first have to understand what temperature really is. And I want you to try and forget the boring definition you might have learned in science class. Instead, I want you to think of it as this wild, microscopic dance party that's happening inside literally everything around you. All right, here is the absolute key. Temperature isn't actually energy itself. Nope. It's how we measure the average energy of motion. That's called kinetic energy, of all those little atoms and molecules. So when something feels hot, all it really means is that its atoms are in a full-blown dance frenzy. Just check this out. When the atoms are just kind of chillin', moving slowly, the thermometer reading stays low. But as they start to really get going, bumping into each other with more and more energy, that thermometer reading shoots way up. That's all a thermometer is doing. It's basically a dance-o-meter for atoms. Now, we've got a few different ways to measure this atomic dance. You've heard of them. Fahrenheit, Celsius, Kelvin. But they're all just different languages describing the exact same thing. And they often use the freezing and boiling points of water as a universal point of reference. Okay, so if temperature is the state of the dance, then what's heat? Well, that's simple. Heat is what happens when the dance party moves from one place to another. Yeah, think of heat as energy in transit. It's the energy that's flowing because of a temperature difference, and it's always on the move from hot to cold. So it's not something an object has, it's something an object gives or takes. That's a huge difference. And here is the golden rule of thermodynamics. Energy always flows from hot to cold. No exceptions. The wild, fast vibrating dancers in the hot block crash into the slower dancers in the cold block, and they share their energy until everyone is grooving at about the same speed. And that, my friends, is called thermal equilibrium. So let's nail this down once and for all, because this is the crucial difference. Temperature is what an object has. It's a snapshot of that atomic dance. But heat is what an object does. It's the transfer of that energy from hot to cold. If you get that, you've pretty much got the key to this whole thing. All right, so now that we know what heat is, energy on the move, how exactly does it get from point A to point B? Well, it turns out there are 3 main ways it gets around. First up, we've got conduction. This is just heat transfer by direct touch. See how the flame gets those atoms on the left vibrating like crazy? Well, they start bumping into their neighbors, who then bump into their neighbors, and so on down the line. It's a microscopic domino effect. This is exactly what happens when you accidentally grab a hot pan handle. And believe it or not, you can see all 3 of these methods working together in one super simple, everyday example. Just boiling a pot of water. The burner heats the pot through conduction. As the water at the bottom gets hot, it becomes less dense and rises, transferring heat in a process we call convection. And the burner itself, it's giving off heat as radiation. All 3, right there. So just to recap, the 3 ways are conduction, which is heat by direct touch, convection, which is heat by the movement of fluids, think weather patterns or boiling water, and finally, radiation, which is heat transferred by waves. This one is so powerful, it can even travel through the vacuum of space, which is how we feel the sun's warmth from 93 million miles away. So, this brings us right back to our spoon puzzle. If conduction is just energy moving through a material, why is it so much faster in a metal spoon than it is in a wooden one? Well, it turns out that not all materials are created equal when it comes to transferring heat. Some materials, like most metals, are amazing thermal conductors. You can think of them like a superhighway for heat energy. But other materials, like wood, glass, or plastics, are insulators. They're more like a traffic jam for heat. It moves, but very, very slowly. And there it is. That's our answer. The metal spoon feels so much hotter because it's a fantastic conductor, zapping the soup's heat directly into your hand almost instantly. The wooden spoon, on the other hand, is an insulator. It slows that heat transfer way down, which is why it just feels, well, warm. Mystery solved. But hold on, there is one more crucial piece to this puzzle. It's not just about how fast heat moves, it's also about how much energy it takes to change something's temperature in the first place. And for that, we need to talk about the secret ingredient, specific heat. So, specific heat capacities sounds complicated, but it's really just a measure of thermal stubbornness. It tells you how much energy you have to pump into 1 kilogram of a substance just to raise its temperature by a single degree Celsius. The higher the specific heat, the more stubborn it is about changing its temperature. Take something with a high specific heat, like water. Water is an absolute energy sponge. It can soak up a ton of heat without its temperature changing all that much. But then you have something with a low specific heat, like most metals. They take very little energy to heat up, and as a result, they heat up and cool down in a flash. And this single property, it has massive consequences for all of us. It's the reason oceans and big lakes take all summer to warm up and all winter to finally cool down. That's what gives coastal cities much milder climates. And get this, it's also why our bodies, which are mostly water, are so good at maintaining a stable internal temperature. It's incredibly important. So you see, from the vibration of a single invisible atom all the way up to the climate of an entire continent, it's all connected. These fundamental rules of thermodynamics are running the show behind the scenes pretty much everywhere, all the time. All right, so now you know the 3 ways that heat moves. Here is a final challenge for you. A vacuum-sealed thermos is specifically designed to stop heat transfer. So using what you've just learned, can you figure out how it stops all 3 methods: conduction, convection, and radiation? Think about it. Thanks for joining me.